Phase diagrams are a very, very important part of understanding materials, material properties, their structure, how things work when we're making materials, when we're letting things solidify. But I'm going to go through this relatively quickly. There's actually a whole lot to go over, and I'm just going to touch on key pieces here and there. As far as where the majority of your learning is going to come on the phase diagrams, in class we're going to have an activity where you're going to make sure that you know some of the terms. You're going to look at some phase diagrams that I give you, and you're going to pull some information from them. I'm going to have you build your own phase diagram with some information that I give you. And then there will be a part towards the end to look over some additional notes on the lever rule, which we'll talk about at the end of this video just a tiny bit. So you've probably seen phase diagrams before, probably in your chemistry class. A phase diagram shows what phase or what structure something has depending on certain conditions. A phase is going to be a region of material that is chemically uniform and physically distinct from other parts or other ways that that chemical could be. So one thing that we sometimes look at is we look at H2O, water. All right, we have normally two axes. This is a two-dimensional plot. On one, we put pressure. On the other, we put temperature. We have 2 degrees of freedom here to kind of see what happens. What happens as the temperature increases, but also what happens as the pressure increases. And so we could have something, let's say, that kind of looks like this. This isn't perfect. This would be like your solid, your liquid, and your gas. This would be something like water. Don't think that I actually tried to draw the structure of water, the water phase diagram here. But this is probably what you're used to seeing, something just with pressure and temperature, and we have phases, solid, liquid, and gas. What we're going to look at is we're going to actually look at binary systems. One axis will be the composition percentage, maybe the weight percentage, the atomic percentage. It's going to be the composition. What is our material made up of? Which means we're only going to have one axis to manipulate the outside conditions that we can control. And what we're going to do is most likely always use temperature. Unless we're doing something in extreme pressures, a lot of times when we're just mixing materials, we're doing it at atmospheric pressure, so we can just consider our pressure to be at 1 atmosphere. If we did want to have this binary system with temperature and pressure, it would turn into a 3-dimensional graph. It would get a lot more complicated, and for me, it would be very, very difficult to draw. So we're just going to stick with a binary system here. I'm going to go ahead and draw. I'm going to go ahead and I'm going to put 2 of them in here. I don't necessarily need the arrow on that one. What I'm going to do is I'm going to say this is our temperature. And down here, this is going to be our composition. I'm going to put C. And by composition, for this example, I'm going to say that I'm talking about the percent of B in A. Now, A and B would just be the things that I'm mixing together to make my material. So this would be 0% B, which would then mean that all of my material is made up of whatever A is. And if I go all the way to the other side, then I'm 100% B, so there'd be no A. I'm only talking B. So what exactly is A and B? It's whatever you want. I could say that my A is iron and my B is nickel. And so if I'm all the way over here to the left, what we'd be saying is we're saying we have pure iron because I have 0% of nickel inside of it. If I go all the way to my right, I have 100% nickel and no iron. And so what I can do is I can look other places, and in the middle it'd be 50-50. 50% iron, 50% nickel. And like I mentioned up here, that could either be a weight percent. I could weigh out equal parts iron and nickel, or I could look at my atomic percentage, equal number of atoms of iron and nickel. And so the shape of the phase diagram is not going to change, but where the lines down here on the bottom axis, my composition, those are going to change. All right, now this one that I'm going to draw is not the iron nickel one. I'm just going to do a very basic one. We're just going to call one component B, one component A. And I'm going to just draw, got ahead of myself. That's going to be our second one that we draw. Let's say that this is my phase diagram. It looks relatively simple. As temperature is really, really high, so as I go up, things tend to melt. And so the very top here is going to be our liquid. And liquids really aren't that exciting to material scientists. I mean, they are to a point, but we're really focusing on solids. And so as we cool, as we go down down from that axis, our temperature axis, we're going to have our solid phase. What we have in the middle is we have this area, this bubble in the middle, that's actually going to be a mixture. We have our liquid plus our solid. It's going to be half and half. What we can do is we can say, all right, let's say we're right here, and this is at, let's say, 20% B. What I could do is I could draw a line through here, and I could tell you exactly what temperature it's going to turn into complete liquid. Anything above that, it's 100% liquid, molten, whatever you want to call it, if it's metal. I have a temperature down here where anything below it, it is 100% solid. And then I'm going to be able to say anywhere in between there, I'm going to have some type of mixture between liquid and solid. Let's say at this temperature right here, I have some liquid, I have some solid, and I'm at 20% nickel and 80% iron. So I can start getting a lot of information from here, especially if I want to do something like look at a specific alloy, a specific type of material. A couple things that I just wanted to mention real quick before we get into another picture, something maybe a little bit more complicated. This is just the very, very basics. A little bit of terminology. There is a liquidus line, and a liquidus line is simply the line where on one side of it, normally that's going to be above it, there is a pure liquid. And so for us, this solidus line is going to be this gray line that I'm filling in here, because on one side of it, I have a pure liquid, namely above it. So that's my solidus line. That's my liquidus line. I also have a solidus line, and a solidus line is just the opposite. It's where on one side of it, we have only solid, no liquid at all. So our solidus line would be down here. On one side, normally below it, we're going to have all solid, and above it we can have something that isn't a solid, but we normally have some solid mixed in. So this above it we have a liquid plus solid, and below the liquidus line we have a liquid plus solid. So a liquidus, only liquid above, solidus, only solid below, and in between those we have some type of mixture between liquid and solid. There are going to be some other terminology that we might mention throughout the video. There are definitely going to be things that we'll talk about next week in our lecture, in our class. I'm going to make another one. We're going to have temperature again. I'm going to have my percent B. And again, B is just whatever I want it to be. It could be aluminum, it could be copper, it could be, it doesn't even have to be a metal. It could be carbon, it could be silicon, it could be phosphorus, it could be whatever I want it to be. That's just saying whatever I'm adding into my pure material, which is whatever A happens to be for this graph or this diagram. All right, I'm going to make one that's a little bit more complex. And here's a phase diagram. This is a pretty simple phase diagram still. Phase diagrams for solids tend to be very, very complicated. If we scroll up really quick to just the phases solid, liquid, gas, they're normally pretty straightforward. I have three regions, one for solid, liquid, and gas. When we get into solids, I think I have one pulled up here. This one's just for water, for ice, for solid ice, H2O. You'll see off to the left here, we do have our gas, we do have our liquid, and then we have ice, and we have a whole bunch of different ices. We have ice 1, ice 2, ice 3. We have a whole bunch of different types of solid ices, and each one of these has a unique structure to it. It has a unique phase, and that's why we give it a different name. So this is still a pretty simple one. But what I want to do is I want to fill out some of the things that we have going on. We have our liquid again up top because as things get hot, they melt. And instead of just having a solid down here, I might have a mixture of solid phases. And so instead what I'm going to do is I'm going to say, you know what, if we're at a very low percent of B, so if it's mostly component A over here, I'm going to say that we have a phase called alpha. Now I want to be really careful here. This alpha has no bearing on the fact that it's close to composition A. Remember, my A could be anything. It could be titanium. It could be any type of material. So the alpha and the A don't really have any significance. If I didn't want to use alpha here, I could say that it was delta. I could say that it was a gamma, I could say that it was epsilon, I could say it was beta. For this, I just want to keep it simple. I want to use alpha. So I have phase alpha. Now what does phase alpha look like? I don't know. It could be anything. Maybe we'll get back to that in just a second. I'm going to have another pure phase where if I go all the way to the right, where it's mostly B, component B, let's say, wants to make something in a phase beta. So that's just another phase. It's a distinct way that it wants to solidify. Let's go back up here. A phase is a region of the material that is chemically uniform and physically distinct. So alpha and beta are just different. They're not the same thing. They're physically different from each other, and they're unique. All right, so from here, I can actually fill out the rest of it. I'm going to fill it out in green. And what I'm going to do is I'm going to just look at what's between here. So I have these gaps still that aren't named. I'm going to say, well, in between this lobe up to the top left, I have alpha on one side and I have liquid on the other. I'm going to say that this is a liquid plus alpha phase. I'm going to do the same thing if I look at the other lobe off to the right. I have a liquid on one side and a beta on the other. I'm going to say that this is a liquid plus beta. And then what I'm going to do is I can say, all right, well, I can do the same thing in this big spot in the middle. On one side, I have alpha. On the other side, I have beta. So in the middle here, I have an alpha plus beta. If I wanted to, I could figure out where my liquidus line was. Liquidus line would be, I'm going to make it just a little bit darker. Liquidus line would be right here. Everything above it is a pure liquid. Everything below it, you could still have some liquid, but there's some solid. So therefore, my liquidus line is there. My solidus line would be here. On one side of it, I have only solid. On the other side of it, there is some liquid. So my solidus line just separates something that is all solid from something that has some liquid in it as well. So now what we can do is we can look at different percentages. I could say what's happening, let's say, at 5% B. Well, 5% B, almost at every temperature, until we get really, really hot, we have an alpha phase. An alpha phase, let's say for us, I'm going to write this off to the side, alpha phase could be anything, but let's just say that an alpha phase for us would be a body-centered cubic. So that means that when I have just a very little amount of B, or maybe no B at all, I want, or the material wants, to form in a body-centered cubic way. Once I reach a certain temperature, right here, then some of it's going to start to liquefy. And as I continue to move up, more and more of it is going to turn into a liquid. But I'm going to retain some solid in there until I reach the very top, until I reach this liquidus line, in which case, if I get above that, everything is liquid. And I don't have any type of solid structure. It's not body-centered cubic. It's nothing, because it's just liquid. It's the liquid mess of being a liquid, just the components all mixing together, able to move around pretty freely. If we move over here, let's say to maybe 15%, somewhere around there maybe. Let's say this is 5%, let's say this is 15%. I could do the same thing, but at low temperatures, I have a mix. I have a mix of alpha and beta phases. I reach a certain point where when I get above that temperature, again, it's still a solid here, but I get to a point where I have no beta phase left, and it just is going to have some alpha. And then again, it turns into some liquid, and then pure liquid above that. And I could do that for all of these. And at some point right in the middle, at least in the way that I drew it, that dotted line's horrible, but it's going to be an alpha and beta phase, but it's going to transition from one temperature to the next. Just as it goes up that 1 degree, it's going to transition directly into a liquid. It's not going to have this spot where we kind of have this mixture as we continue to increase temperature. I can do the same thing on the beta side. I could figure out at some component, let's say 90% B, I could come in here and I could figure out that we're alpha plus beta for a while, then we're totally beta, and then we'll be liquid and beta, and then again, just liquid. And let's say that beta, again, it could really mean anything. It's just a distinct phase. Let's just say that that is face-centered cubic. So one thing to keep in mind, that if I zoom in on any one of these spots, let's say that if I'm in alpha, I zoom in and look at my phases, they're all going to be alpha. And let's say all my alphas, I'm just going to shade them in as green. If I am, let's say, at about 20% composition, I now have a mixture of alpha and beta. But most of it's still going to be alpha. But I do have this empty region, this region that I'm going to call beta. So if I look at my beta region, they're all beta, they're all not shaded in. And again, maybe at like 80%, 85%, if I look at my phases, I might just have a little bit of alpha, where most of it's still beta, and somewhere in the middle, it's going to be about half and half. Something along those lines. All right, so that's really quick, still a pretty basic phase diagram. I want to get into and cover some phase reactions just really, really quick. These are important to note. I will have some notes available for you. You can write these down yourself, but I do have some notes that you'll be able to look up on Canvas. Eutectic. A eutectic reaction means that we're going to have a liquid, and this reaction can happen either way. It can either happen forward or backwards, right? Because as we increase temperature, it's going to be moving up. As we decrease temperature, it could be moving down. So really this is either way, but this is a liquid goes to an alpha plus a beta. So what I'm going to do is I'm going to look at what's happening actually as temperature decreases. So I'm going to take this bottom one away really quick. So as temperature decreases, we go to an alpha plus a beta. We go from a single phase and we go into a dual solid phase. And our reaction is going to look like this. Kind of what we drew previously. I have my liquid, I have my alpha, I have my beta, I have my alpha plus beta, I have my liquid plus alpha, and I have my liquid plus beta. All right, so the eutectic reaction really is saying right here at this point, what's happening? Well, as I decrease, I go from a single liquid into a dual phased region. Now, again, it has nothing to do with alpha per se or beta per se. These could be something completely different. They could be gamma, they could be delta, they could be whatever. But what a eutectic reaction is, as I cool, I go from a single phase, in this case liquid for eutectic, and I go into a dual phase solid region. And that's really what a eutectic is. I'm going to do eutectoid next. The names are similar, but there is going to be a very important difference. And in this case, what I'm doing is I'm going from a single phase, but in this case, I'm going from a single solid phase into a dual phase. So it's very, very similar, except for I take the liquid and replace it with a solid. Now keep in mind that if we heat up, we get the same thing in reverse. What I'm going to do is I'm going to draw this out really quick. In this case, I have our gamma phase up top, my alpha and your beta. Down here I have alpha plus beta, and here I'm going to have alpha plus gamma and gamma plus beta. So again, as I, or you, or whoever, as we look right here at this reaction point, the point right in the middle, what happens as we move down? We go from a single phase, but in this case it's a single solid phase, and we go into a dual phase, where we have two solid phases. That's the difference between a eutectic and a eutectoid. I do want to point out really quickly that we're going to do 4 more of these, but there are some similarities. All the ones that I have on the left-hand side end in tectic. We have eutectic, we have monotectic, and we have paratectic. All the ones on the right-hand side end in tectoid. Tectoid for eutectoid, monotectoid, and paratectoid. I'm going to let the cat out of the bag a little bit early. Sometimes I write these up and let you guys think about it for a second. But all the ones on the left-hand side, the ones that end in tectic, are going to have a phase that includes a liquid. All the ones that end in tectoid, the ones on the right, are going to have no phases of liquid in them. So now that we've kind of talked about that, and we've kind of said like what we're doing is we're going through our reaction point, the point in the middle where everything kind of meets together, all these lines meet. I'm going to go through these ones really, really quickly. I'm just going to draw them up. Like I said, we can look at those more in class. All right, monotectic. I have a liquid that goes into an alpha plus some liquid as well. This is going to look strikingly similar, but I have my liquid 1, I have my alpha, I have my liquid 2, I have my alpha plus liquid 2, here I have alpha plus liquid 1, and here I have liquid 1 plus liquid 2. So again, I have this point. I didn't draw it really good. There's a point right here. As we move down, we go from a liquid to an alpha plus liquid. There is liquid involved. It's a monotectic. I have monotectoid. We go from some solid phase. In this case, we're going to say that this is an alpha 2. And we're going to go into an alpha 1 plus a beta. The shape's going to be the same. It's just going to be what we put in here is going to be a little bit different. Alpha 2, alpha 1, and beta. And I can fill in what I need to know. All right, then we get into the paratectic. Paratectic, we have started a dual phase as we cool. We have a liquid plus beta, and we go into a completely different phase. Kind of looks like an upside down eutectic. I'm going to have my liquid here. I'll have a liquid plus beta. I'll have my beta. I'll have my alpha, and so here I have a liquid plus alpha. I have an alpha plus beta, and again my reaction point's right here in the middle. And then a paratectoid is going to look exactly the same, except for no liquids are involved. I have a two-phase region, and it's going to go into a single-phase region. We have our alpha, beta, alpha plus beta. It goes into a gamma. I'm going to move this over here. That alpha is part of the phase diagram, not part of the reaction. Alpha plus gamma, gamma plus beta. So we can look at those a little bit more in class. I just wanted to kind of get them up there. Those are some important ones that we're going to discuss and use. And I mentioned that we're going to talk a little bit about the lever rule. I'm going to just touch on this really quickly because I'm going to want you guys to go over this a little bit in class when we talk about it some more. There's actually a video that I found online that goes over the lever rule really well. And I have a link to that video that you guys can watch in class. And what I did was I wrote some notes from the video. So again, kind of showing you how you can maybe take notes as you watch videos as well. This is on the lever rule. And really what it is as I have something in a phase diagram, this goes back to the very basic one. But what happens when I have a component inside of a mixed phase? And it could really be any type of mixed phase. If we go back to here, we could be looking at in an alpha plus beta phase, we could be looking at a liquid plus beta, we could be looking at a liquid plus alpha. The one we're going to be looking at would just be a liquid plus some solid. What we're going to do is just quickly, I have 2 pages of notes here. I'm not even going to go over them really that quickly, or I'm going to go over them really quickly. I'm not going to go over them in depth. But what you do is you use the lever rule. Lever rule means you draw a tie line, and a tie line is a horizontal line that goes from a solidus to a liquidus, or just basically from one beginning of a region to the beginning of the next region. And what we want to do is we want to figure out the ratio of one side. So really, if I drew this really carefully, I could just get a ruler and I could say, what is my length A compared to my total length C, or what is my length B over my total length C? And that's all the lever rule is. It's a simple ratio. And what this ratio does is it tells us inside of this system that if I have this spot right here at this concentration and at this temperature, how much in this dual phase region is solid and how much is actually liquid. And so we go through, we do a mass balance, and this is all covered in the video. We can talk about this in class as well. But all a mass balance really is I have a mass of component B, let's say, And it's either liquid or it's solid. It can't be anything else. So if I sum up my mass of B that's liquid and my mass of B that's solid, that gives me my total mass of B. We can do some substitutions, do a little bit of algebra, divide some things through, do some more substitutions. And again, you don't necessarily have to understand this all right now. We can watch the video, we can talk about it in class. And then I simplify some things. I like to use absolute values in my final answer, just because if I miss the sign somewhere, it doesn't make any sense to have a weight percent, and that's what we're really getting at here, is what weight percent is in one phase compared to the other. But really it gets down to exactly what I said. If I could take a really good measurement, if I took that length A and divided it by total length C, that would tell me what my solid is. And if I took my total length B divided by C, that would tell me my total liquid. There are a couple things to think about right here, and so I added these down at the bottom. I like to use extreme cases to really understand what's happening. The question here is, well, which one of these is going to give me my solid and which one's going to give me my liquid? Let's say I was just grabbing these equations and I wasn't sure which numbers to plug in where. What I would do is I would look at my picture. And if my picture is down here and my intersection is down near my solidus line, then I know that I have more solid in it than I have more liquid. That just makes sense. I'm closer to my solidus, I'm closer to my solid region, which means that I should have more solid. In this case, what that means is to get a bigger number, if I take this length A and divide it by my total length, I'm going to get a number pretty darn close to 1. And so really what you're going to do is you're going to take the portion of the tie line that's furthest away from what you're trying to find. In this case, it's my solid. I'm going to look at the thing that's furthest away, which is A, and divide it by my total length. If I want to do my liquid, I would take the thing furthest away, which is B, and divide it by my total length, C, and I'd get a really small number. I have a very little bit that is liquid. So just another way to kind of think about it. Another way, especially since I know we have a lot of engineers in here, is we could look at this more from something maybe you've done previously, such as a mechanical system. If I was trying to balance something, and I had my fulcrum here, that's wherever I drew this line through this tie line. So I kind of have this balance going on here. We could use this same idea to figure out our weight percentage. How much weight do I need on this short leg so that it stays in equilibrium? Because I have this long leg with the weight attached as well. I need to make sure that this stays balanced. And so on a short leg, I'm going to need more weight. And on a long leg, I need less weight to make sure that it stays balanced.